Testing, testing, 1, 2. Okay.
Hey, good evening to all of you. So if I can have your attention for a few minutes, continue to eat. We'll just do a few announcements here and then get to our dinner meeting. So welcome to the November meeting of the STS-AIChE. I'm Ramanand Krishnamurthy. I'm at the University of Houston, also the chair of the section for this year. So for those of you interested in PDH certificates, definitely do send us an email. Send me an email, and we'll make sure to get that to you if you've not already ticked for it in your in the invitation that you filled in. So very quickly, what we're going to do today, work through a few different program items, mainly talk about the awards, elections, and the next dinner meeting. So with that, let me invite Tom Mann to come up. I know that I caught him at the wrong moment, but Tom, if you're ready, we can get to the awards. So as Tom comes up, let me very quickly tell you, you can nominate folks for next year's awards. And there are 6 categories in which you can nominate people. The best applied paper, the best fundamental paper, the best in-practice paper award, 3 different paper awards, an outstanding young professional under 40. You have to be an STS member. STS Distinguished Service Award, over 36, and STS Special Awards. There are several of these that are given out periodically. With that, Tom.
Thank you.
I grabbed it. I got it.
Oh, you got it. Okay, move this thing up.
You want to go back?
One more. No, forward.
One more, okay.
Okay. Okay, good. I don't need my glasses. Okay, the South Texas section annual Distinguished Service Award for 2020 is Tom Ream. He's the fellow of AIChE and a professional engineer in the state of Texas. He grew up on a small Arkansas farm with 40 acres of soybeans and 100 head of cattle. At the age of 14, Tom's dad said he was going to leave the farm to him. So he decided to buckle down in school as he had enough of farming. As I told Tom, you can make a small fortune in farming, provided you have a large fortune to start with. You have to grow up on a farm to appreciate that. After graduating from high school in 1968, Tom attended Arkansas Tech for 2 years, where he encountered organic chemistry and decided he would never be a chemist. So he transferred to the University of Arkansas, receiving his BSCHE in 1972. Tom went to work for UOP in the Chicago area. In 1978, he decided to get his MSCHE and started taking evening classes at Northwestern while continuing to work. In 1981, Professor George Bancroft, a Manhattan Project alum, convinced Tom to pursue his PhD. In 1982, Tom got his MSCHE and his PhD in 1985, both from Northwestern. Tom went to work in 1985 at Amoco, now BP, and Research Center in Naperville, Illinois, until 1992. 1993, Tom took his family to Kingwood, Texas, joined a consulting firm specialized in industrial accident investigation for litigation. From 1997 to 2008, Tom worked in Saudi Arabia's loss prevention department. Saudi Aramco's loss prevention department was used on the steering committee that established Saudi Aramco's process safety management program. Tom led the development of the incident investigation element. Tom admits to having little involvement in AICHE through his career. In late 2014, he decided to become active with an ulterior motive to network to increase his consulting work in process safety management. In late 2015, he was elected to STS Human Resources Officer as position 4. In 2017, he was elected STS Chair-elect. 2019, he made the Global Warming Solutions the STS theme. October 2018, Tom and 3 colleagues convinced the AIChE Board of Directors to approve a new community called the Climate Solutions Community, or TCSC, whatever. The first TCSC meeting of this 12-member management board was held on September 21st, 2021. In 1981, Tom married his wife, Mary. Tom had 3 kids from his first wife, who passed away in 1979. Mary had 2 kids from her first husband. They were a Brady bunch. Tom and Mary have 10 grandkids, 6 living in Texas and 4 in New Zealand. Tom likes to shoot pool, and if you can run a table of 8-ball and 9-ball, he challenges you to a friendly game with financial stakes. Congratulations, Tom.
And I'll embarrass you even further with what we did together. So just so that if people haven't seen this, it's probably worth, Tom's been somebody who has taken a lot of interest in advancing the South Texas's position and the chemical industry here. And so when Winter Storm Uri hit, Tom worked with me, Julie, as well as with Victor here in putting together this op-ed that appeared in CEP in October, and something that we all put together. But really, Tom was the driver for much of this information that got put together. He is continuing to remain dogged about how Texas will respond to Winter Storm Uri and beyond. And that's something that really takes commitment, takes vision, and takes real insight in doing. So Tom, thank you for what you do here, and really appreciate all your leadership in this area. Thanks. So all of you should probably pull out your cell phones for what is up here, as you see. We have an election that is currently ongoing for both secretary as well as position 2. Position 2 is for the education component of the 4 positions that are in STS-AIChE. We have 1 nomination in each of those, and the tellers would like for as many votes to be put in for either these candidates or for alternates. You must have received an email with that link, but if you don't, the link is up there. I'm going to let it, it's fairly straightforward with all the dashes and commas, and so, but that aside, it is something that if you can do it, the election will be open till later tonight. There's one other position that we are trying to fill. Mark Harkness has been dogged about that and trying to get position 4 filled, and we are looking for nominations. So if you've got ideas for nominations for position 4, certainly be interested in hearing from you. Lastly, I want to introduce, for those of you who've not already met Andreas, Andreas is the chair-elect. Andreas, please get up and be recognized. He was recently elected as the chair-elect for STS-AIChE. So 2022, he'll be chair-elect. 2023, he will be the chair of the division, of the local section. So with that, I think we get to the main part of our program. And our guests have finished their dinner, thankfully. I didn't want to get them to stand up before we were ready. So today's story that you're going to hear about is an absolutely fascinating story about Cemvita Factory. Cemvita Factory, probably most of you have not heard of them at all. But they are what the future of Houston and the energy industry is going to be. And just simply put, they are working with the pioneering chemicals industry and developing synthetic biology methods and applying it to challenging problems that address sustainable solutions. And so they have got, so the lead speaker today is Roger Harris. Dr. Roger Harris is the CTO of Cemvita, and he's here with his team. And the team is Trong Wen, Kevin Kincaid, and Matt Shapiro. I'll let Roger introduce them to you, but really it is an incredible story that you should all sort of pay attention to, because this is the kind of disruption that is ready and coming to the chemical industry. And so with that, let me just very quickly tell you who Roger is. Roger, as you will recognize from his accent very soon, was educated from South Africa, and that accent is very, very clear. But he's a PhD. He's a PhD in chemical engineer, but has worked in sort of the pioneering areas of chemical engineering, sort of startups. Velocis is a place where he's worked. He's had a long experience in Sasol, and he's got a whole bunch of publications, patents, and conference presentations. We're all ready for you, Roger. So when you're ready to get started, we'd love to have you up here. And there's dessert for anybody who's interested in dessert. Grab dessert and make yourself comfortable for, I think, what is going to be an absolutely fascinating talk.
Thank you so much for the kind introduction.
Yeah, absolutely.
Thanks. Good evening, everyone. Thank you very much, first of all, for the invitation to be here this evening. There we go. Thanks. When Matt gets here, you're going to have to lift it about another 2 feet. Thank you very much for the invitation to be here this evening. We really appreciate it and appreciate the kind words in the introduction, and look forward to the discussion tonight. I just want to admit that I haven't had a surprise promotion to my team over here. I'm still just the VP of Technology Commercialization, not the CTO. We have a very competent CTO who is also our co-founder, so she'd be very upset if she found out that I'd usurped her. So what myself and the rest of my team would like to do this evening, and beg your indulgence in doing so, is really just take you on a bit of a trip with us into the future and have a look at that future that Ramanan mentioned in the introduction, the future of our industry and where we as Cemvita want to grow our company to be. So maybe before I get stuck into the future, I wanted to just take a pause and have a look at where we are today. And I think no matter where we come from, no matter which part of the scientific debate we sit on, we realize that at the moment we sit in an era and in an industry that is really at the center of a perfect storm. And this molecule pulling us all into that maelstrom at the center of that perfect storm is CO2. We hear about CO2 on a daily basis. We hear about it from activists, such as the one up in the corner there. We hear about it from rogue and guerrilla investors that have managed to take control or take managing positions on some of the largest boards in the industry. And we also, as an industry, are definitely going to feel it in our operating costs, as can be seen just in terms of the cost of carbon across the industry, across the world. And so what we really want to say is when we look at CO2, we realize that at the moment, no matter how you see it playing out in the future, from a pragmatic point of view, it is a real threat to some of the largest and most productive industries that are currently in operation. Oh, I think this is kind of... There we go. Oh, no, other way. Thanks. Great, that's fine, that's fine. Thanks. So, sorry. As I was saying, we see CO2 as being at the center of the industry and being a real threat for all of the players within the industry. And, you know, to move away maybe from the dramatic slide and into a little bit more of a quantified one, we have a lot of organizations out there. COP26 is currently in process. The IPCC itself estimates that we'd be required to pull 100 gigatons of CO2 out of the air net by 2100 to be able to target some of the 1.5 degree Celsius targets that have been set. So that means not just eliminating what we're currently producing, but actually pulling that CO2 out of the air. Currently, as we stand today, the industry on which we all rely for transport, for materials, for general energy, currently contributes a third of the annual emissions into the atmosphere, roughly 10 gigatons. What we as Cemvita are really focused on doing is taking that CO2 that currently resides in everyone's mind as a threat and a weakness on the SWOT chart, and what we really want to do is move that away from the threat and weakness side into a potential opportunity and eventually into a strength. So how do we plan to do this? And I'll give a very brief introduction. As Ramanan said, I'm a chemical engineer, and so what we're going to speak about tonight, I'm not qualified to speak about. Fortunately, Trong on my team is. But essentially what we're looking at is really trying to harvest an exponentially growing industry, and that's the industry of genetic engineering, which 20, 30 years ago when we first heard about it, the concept of even being able to decipher the human genome was a project that took years and millions, billions of dollars. Today, you're able to spit into a jar, send it across with UPS and find out what your genetic makeup is a couple of weeks later. So the cost of analyzing DNA has come down exponentially. The ability to manipulate it has come down exponentially. And scientists like Trong have really found ways in which to use that to our advantage. So what Cemvita looks to do is take CO2 that was once a liability and a threat to industries and use that as a feedstock. That feedstock can then, through microbes, be converted into products. And what specifically differentiates us in that journey is to really have a look at producing products that are within the existing value chain of companies. So a lot of renewables create a new product. That new product then requires shutdown economics for the existing value chain, as well as requiring end-user adoption of it. What we really focus on is providing a product that already has end-user adoption and would allow customers a seamless transition by utilizing the majority of their value chain. So what we'd like to cover this evening, I'm going to take a couple of minutes just to introduce the team, and then I'm going to hand over to Trong to really give all of us a sense for what is synthetic biology, where's it come from, where's it going, and what is it going to enable. Trong will then hand over to Matt, and Matt, as you saw earlier, has a background in project management, and what we're really doing at Cemvita is utilizing that skill set that he brings from the industry and using it not just to scale up our processes, but also to scale them across multiple product lines. And then finally, we'll have Kevin talk us through the commercialization process and specifically how do we commercialize something like this, which is a disruptive first-of-a-kind technology. So thanks. I don't think I have to do any further introductions of myself. In fact, you did a lot better job than I would have been able to do, so I appreciate that. Dr. Trong Nguyen, who's part of our team and is actually employee number 4 or 5 at Cemvita and has been there since almost the inception, has a synthetic biology background. He's recently moved into the business development team, and between himself and Kevin formed the core of that team's leadership. But prior to that, he was head of synthetic biology for Cemvita, and a lot of the case studies and the existing processes we're going to talk about today came into Inception through his leadership. He has background in synthetic biology up to the PhD level and has numerous publications as well as patents in that area. As I said, Matt, who will speak a little bit about our scaling process, has a background in project management. He's worked extensively in oil and gas, delivered more than 20 oil and gas projects across a global playing field, and brings a lot of that learning, but also some of the new software type of skills that are really going to help us leverage that scalability. And then lastly, Kevin, who's part of our team, has a deep background in patents and developing new technologies. Kevin's been part of several startups previously and taken them through the commercialization curve. I think like a lot of us who've been along first-of-a-kind technologies, he understands the warts and also the punishment that comes in terms of doing that process, but has done it several times over and will be instrumental in Cemvita's pathway to commercial success. So with that, I'm going to ask Trong to start us off with what is synthetic biology.
Thank you, Roger. Hi, everyone. So thank you for coming for the meeting. So I think first of all, I just kind of talk a little bit about kind of synthetic biology. So what is it? Because it's kind of the core technology that Cemvita is based on. So in short, I would just say synthetic biology is kind of a collaboration between kind of biology field and the engineering field. So the question is like, is that going to be something like this, where you kind of apply kind of a biology mindset into kind of engineering, right? So something like an airplane, but it's not, right? So synthetic biology is to kind of to apply what we call an engineer approach, engineer framework into the biological field. The engineer framework and approach is that like by we using kind of like standardized biological part, we use kind of like computer-aided experimental design, and we use some of tool in engineering, for example, like automation, to kind of like significantly accelerate the technology development in the biological field. So when you look in the graph there, it's just kind of like an example of kind of like the synthetic biology framework, right? For example, when we kind of engage with the client, and then we kind of identify what is the chemicals or the process that we want to develop, we go to kind of like the design phase. In the design phase, what we use is we use some of the tools like bioinformatics, data analysis, to kind of like identify the pathway, the set of the reaction that can go from CO2 to the target molecule that we want. And then we also kind of like select the host, like the right type of microorganism that we're going to engineer on. And then we also design the biological parts like gene and protein in the computers. Once we finish the design phase, where we go to the build phase, where we kind of like we carry out the microbe engineering, where we kind of like adding new capability into the microbe. And this is where some of the engineering tools, for example, like automation, will help us kind of like speed up like the development process. When we finish with the build phase, where we go to the test phase, where we use kind of like analytical kind of method, for example, like gas or liquid chromatography, so we can confirm that the modified microbe that we make produce the right molecule that we want, for example, like ethylene. And then from there, we can also measure the productivity, the yield, and also some of the byproducts of the process. And so if we satisfied with the result, then we go to the scale, where we kind of like scale up the production volume and eventually commercialize our technologies. And then so Matt and Kevin will tell us about like how we can go from like a lab scale to kind of 1,000-liter bioreactor in a very short timeline. But if improvement is needed, then we can go to the learn phase where we can kind of like redesign our process, redo the data pathway analysis. So basically, by applying the engineering mindset framework, we create kind of like a cycle where we systematically and consistently improve our technologies. So how did we get there? So kind of like a little bit about like the development of synthetic biology, right? So in some case, some people may say like synthetic biology have a very short development, starting with like the creation of like Frankenstein, right? But actually it happened like way longer than that, right? So if you look at the picture here, is on the left is the corn ancestor, and on the right is the modern corn we have today, right? So through selective breeding, our farmer have improved corn from a grass until kind of like a big sweet staple food that we have today. But they do it with very little information on how they can improve the corn, and that's why it takes us more than like 9,000 years to go from like the ancestor corn to the modern corn that we have now, right? And then only from in like 19th century, where we start kind of like understand more about, for example, like the law of genetics, where we understand how kind of like, for example, the characteristic of a parent can influence the offspring, right? So kind of like have a bit more systematic understanding on kind of like the genetics. And then only in the mid-20th centuries, where we kind of like elucidate kind of like the DNA structures with the recipe of all of our kind of like characteristics, all of our capabilities. And then only the last 20 years where we successfully finish the Human Genome Project, right? And then from this Human Genome Project, that is kind of like open a books for us to kind of like understand how biological system work, how our body function, how some of the disease like cancer or diabetes like impact us, right? And then only recently, we developed some of the tools, for example, like CRISPR and Cas9, where we can precisely modify the genetic material inside the microbe. And that kind of like usher a new era of synthetic biology and biotechnology. An important development also kind of like the significant enhancement in our capability for like sequencing and synthesis genetic material like DNA, right? So 20 years ago, it took us $3 billion and 10 years to sequence the genome of one human, right? Nowadays, if you have coupons, it costs you like $1,000 and a week to sequence your whole genome. And with that, you have way more information about yourself than any point in the history, right? So we start from knowing very little on how to improve the corn to now is like we have both the knowledge and also the capability to kind of modify the biology system to improve, to achieve what we need. And that kind of like some of the recent achievement help synthetic biology and biotechnology to get out of, healthcare and pharmaceutical industry to go into kind of like commodity and heavy industry like oil and gas or mining. And that is what Semita are trying to do. So the question is kind of like, okay, how can we modify the microbe to gain new capabilities for the heavy industry? So the process it's simple enough, right? So the bacteria, they have kind of like two sets of DNA. One is for kind of like basic function for the microbe. And then the second set of DNA is what we call plasmid or vector. So these plasmid and vector help the microbe to gain new function from when they try to adapt to the new environment. So with the tool that we have now, we can take that vector DNA out, and we can cut it open, and then we add a donor DNA into it. So the donor DNA carry a gene that help the microbe to gain new function. For example, like to produce ethylene from CO2. We put that back, we ligate it back, and then put it back into the microbe. In this case, is E. coli. And then when the E. coli grow, it creates like a clone. And then we can take that clone, we put it in the bioreactors, and that help us kind of like convert CO2 into the ethylene. That's simple enough. But that is just kind of like one step within kind of like the whole Cemvita process. So again, so we start with CO2. We identify the pathways, that the optimized pathway to go from CO2 to the molecule, the target chemicals that we want. And then we genetically engineer the microbe to achieve that. And then when we scale up, we apply some of kind of like chemical process. So we develop like block flow diagram, process flow diagram, and then we also do kind of like techno-economic analysis to make sure that our technology not only feasible, but also economically viable, because we want our technology successfully compete with the traditional method. And we do it within our brand new facility, which is like only 10 minutes from here. So the pictures from our facility, our lab. So here is kind of like where everyone kind of like work and collaborate. At the bottom here is kind of like Kimberly doing kind of like genetic engineering of the microbe, and then we have also a facility where we store, maintain, and we grow and optimize the growing condition of this microbe to enhance the productivity and to achieve like, and then to scale up our technology. So that's it. And then now Matt gonna talk a bit about kind of like our platform and then how Cemvita process. Thank you.
Thanks, Trong. So, you've heard a little bit about, to circle back to the process that Trong was speaking to. Is that my... You just bring me a chair, it's fine. Okay, thank you. Yeah. So, Trong showed a diagram earlier about our process, our cycle of design, optimization, scale, and commercialization. He spoke quite eloquently about our design and our optimization process that happens in the lab. And now I'll walk you through a little bit of how we scale that up and scale that across and build that out into a commercially viable venture. One of the first tools that we use for scaling across is bringing, and as Roger pointed out, I have a background in oil and gas software. So bringing a software project management structure to that process, we use Scrum Agile, which is a process that's founded on rapid iteration, rapid feedback, and a quick cycle time. So we create a set of features, we bring that in, and we work across functional teams to engineer, to design, to gather feedback, to gather experimental data, and then to analyze that in an engineering context and in a client context and ensure that the products that we're creating are targeting the correct molecular pathways and the correct economic factors. That feedback process also lets us transmit that capability across our teams so that we can we can mix and match engineering and scientific teams across disciplines and share a lot of this kind of functional quality throughout our organization. We've also started to launch our pilot facility, And the pilot facility is very exciting for us. This is what really takes us to extend the software analogy into full stack synthetic biology. So we are taking an idea and we are translating that into a plasmid, we're translating that into an organism, and then we're scaling it up through the lab scale, through that iterative process, and creating a 100-liter or 1,000-liter experimental setup. And this allows us to engage not only in proof of concept, proof of our biological pathway, but also proof of process, so that we can demonstrate the electrical requirements, the heat requirements, the facility requirements that are going to be the foundation of the economic demands that our processes require. And that lets us perform data collection at scale, gather that information, do requirements analysis, and gather additional feedback from our clients that lets us point toward issues of pH, issues of temperature tolerance, and other things that aren't necessarily direct impacts on our molecular pathway, but have huge impacts on the facility that we're designing. And that's the first kind of step in that scaling up process and turning this from something that's effective at a laboratory scale to something that's effective at a commercial scale. And these are images here of our current pilot facility. A couple of reactors that we have are 1,000-liter photobioreactor, where we're pumping light into these organisms and converting ambient CO2 into biomass and sugar. And also a fermentation reactor, where we're taking that sugar and those useful products and translating those into products that can be used for feedstocks. So how does this all come together? Again, we start with the phase one, our demonstration, proof of our molecular pathway, and that ability that Trong spoke to of our scientists to take an idea for carbon use and turn that into a functional molecule. Then we go through that scale-up process, and we translate it into that 1,000-liter pilot reactor. We get it ready for commercialization, and Kevin will speak to how that commercial process works and the impacts that we foresee it having on the industry. But to recontextualize this in terms of our discussion of the history of genetic development, that process that Trung was speaking of, that that 9,000 years of turning this grass into one of our staple foods, we can now do that in a matter of months or years, where we can, in less than a year, we can take an idea and convert a wild existing microbe into something that can be purpose-built for heavy industry. And in another year, we can take that and scale it up to a commercially viable process that we can demonstrate in our pilot facility, that can then be rolled out and deployed across huge swaths of heavy industry and have tremendous knock-on impacts, which Kevin will speak to.
Sorry, I mean, we shouldn't have put Matt in the middle. He should have gone last. Thank you. So I want to thank Trong for kind of explaining the technology to us and what it enables us to do with these organisms, and Matt for showing us within our facility how we scale this up. But looking towards the market, where do we actually see ourselves applying this technology? What we see is we've identified 3 areas mainly where we can start to apply these techniques and this know-how in order to make an impact. And that's in carbon capture and utilization. We are also exploring subsurface utilization of carbon. And then lastly, we're looking at the mining industry as well. So I'll walk through a couple of these and let you know how we see ourselves approaching it. So the first one is the carbon capture and utilization. And what we envision here is, a way to start to displace fossil fuels, but still maintain the same products within the value chain. So with a lot of bioproduced plastics and kind of bio replacements, they're not one-to-one replacements. They're close, but you end up having to change a lot of your value chain in your operations in order to work those bioproducts into your end products. We're designing the microbes so that the ethylene that they produce is the same as the ethylene that is made today. So it drops right into the chemical processes as a viable feedstock. And that's the same for the propylenes, your C4s and 5s, and also for the aromatic fractions. And so it's a way to displace not only the fossil fuels, but to displace a lot of the large unit operations at these facilities that are your CO2 emitters. So you get kind of a double dip effect. Not only are you eating CO2 with the bugs, but you're not running processes that have large CO2 footprints. The other one is looking into the subsurface reservoirs. One idea that we're currently working on and testing out in our lab is using synthetic microbes and enhanced microbes in order to produce clean hydrogen in the subsurface. So when we look at this process in abandoned reservoirs and stranded assets, there's still a fair amount of oil that is left underground. And this is a good food for a lot of these microbes to start to degrade. And they can degrade that and produce hydrogen. They can also produce CO2, but there are methods, kind of known processes, to either keep that CO2 underground or to quickly separate it and put it back into the reservoir at that site. And so when we look at that a little more and we start to look at, what is the potential market for this, there's a large number and inventory of abandoned wells out there and stranded assets. In the US, there's 4 million onshore, close to 40,000 offshore, and in Canada, there's another 500,000. And these abandoned wells is a huge liability, not just financially for the companies that own them, but from an environmental standpoint too. So by converting these into producing assets, it reduces that liability. And on top of that, you can use the infrastructure that is already on place at these spots. And like I said, we're looking at hydrogen, but there's also the opportunity to inject CO2 into these reservoirs and use microbes to convert that CO2 into other end products, whether it's ethylene, methane, or whatever we design the microbes to do. And while it kind of seems like an out there idea to use oil and gas assets in order to produce hydrogen, it's something that's already gaining traction. One thing that's happening right now is that a jackup rig in the North Sea has been converted to create green hydrogen. Green hydrogen is different than what we're trying to do, but it's showing utilizing assets that are in place and that are kind of not being used and repurposing them to produce other chemicals like hydrogen. So the last one to talk about is what we see in the mining industry. So here what we have is kind of like a standard layout for a mine. Your ore goes in to the crushing and screening, and beneficiation, that ore is cleaned up and kind of made much more rich, and then it gets pelletized and sent off for further processing and manufacturing. And the wastewater is sent to the tailings pond. What we see, and what's good about the mining industry is that they already use a lot of biology, and they already use a lot of microbes. So what we're looking to do is to increase what those microbes are already doing, to enhance the crushing and screening, and to improve the separation of the kind of waste materials within that ore with the valuable products. And one of the important things and why this is important is that there's really no more good rocks out there. High-grade ore is extremely rare. So more and more operators and mining companies are going after really low-grade rock, which means it has to be crushed up much finer, which means that your separation and your beneficiation is not as fast. And it means that you use more water in order to process this ore. So you have a much larger tailings dam. So what we are looking to do is to improve the crushing and screening through the generation of biosurfactants that are added into that, and improve the beneficiation, again, through biosurfactants and bioacculation that can happen. And then ultimately, when you improve the efficiency of those first two processes, you don't produce as much tailings and wastewater. On top of that, there's actually a lot of metals that are left in this wastewater. So there's the opportunity for us to also recover those and kind of reduce the size of the tailings footprint. And while I think what's important to point out is how much energy the mining industry uses. Something that's close to 5% of all the energy that's generated globally is used just to crush rocks, not to process them, not to move them around, but literally just to break them. So even small improvements on these processes can have huge CO2, mitigation properties. So looking at what we're actually working on in the lab, Trong and Matt mentioned turning CO2 into ethylene, and that is kind of our flagship project that we're working on at the moment, in partnership with Oxy. I think I'm allowed to say that, right? Okay. And so the way that we're designing this process is to provide a plant and design a plant that has actual real world applicability. So taking 1.7 megatons of CO2 directly from flue gas and turning it into 1 billion pounds of ethylene per year. And so this is kind of a world scale ethylene plant. And we're aiming to do this at parity in costs. And then on top of that, kind of the icing on the cake for this is that because we're capturing CO2 and utilizing it, we would qualify for 45Q tax credits. So that's kind of the additional icing on the cake. We don't want to depend on tax credits. There's a lot of kind of renewable energy systems that are dependent on tax credits. But really, in order for this to work, we have to be at cost parity with, regardless of what the tax situation is now or maybe in the future. And ultimately, we are a company, so we do want to make money. And so the way that we envision it is that we don't see ourselves ever being an owner-operator of any facility. We want to work with customers that are the ultimate end users. And so really what we're doing is we're a technology provider. Much in the same way that a catalyst company provides catalyst, we would be providing the microbes and servicing those microbes kind of as an ongoing service. So when we go through our development, we have the initial phases, phase 1, 2, and 3, are really our laboratory development, scaling up in our facility, and then building a skid-mounted unit that can be delivered to site to be tested at real-world conditions. And then moving forward, we would make money both on the engineering and the licensing fees that once a commercial unit is built. And so on the top one, you show what that looks like for a single project, but we see this as a platform technology with multiple applications, both across those 3 pillars I talked about, but also multiple applications within those 3 pillars. So when you look at having multiple projects at once, what is good about this is because it is a platform technology, that time to commercialization comes down, so you can get through to your licensing and engineering, your licensing and royalties more quickly. And I think I'll pass it on to Roger.
Thanks, everyone. I realize we are getting to the end of the evening, and just want to thank you for your attention and once again for the invitation. We give variations of this, obviously, depending on clients and pitches and interested parties. I had the misfortune to have to do this for a marketing team who none of them had engineering or science backgrounds, and what they really told me was you could pretty much condense all of that into just saying these are GMOs for CO2. But you got the long version of it, not the short version. I think I think we see ourselves as obviously leveraging off a lot of the great capabilities that we find here in Houston. So we are a Houston-based company. A lot of times people say, well, you're in renewables, shouldn't you be on the West Coast in California somewhere? We actually think that Houston and the skill set here is uniquely suited for what we're trying to do. We've got a great facility just down the road, just down Kobe Drive. Trong and Matt showed you some pictures of that. We've actually been growing that constantly since the beginning of the year. In fact, in the last 6 months, we've added more than 30% to our technical and R&D teams alone. Not just that, and once again, my team did a great job of telling you what you're about, but you don't just have to take our word for it. We've recently closed our Series A funding, and have a great group of investors, but we don't just see them as investors, also partners that are going to be partnering with us during this journey. So thank you very much for the opportunity, and obviously open to questions. I'll get these guys to field any of the difficult ones. Thank you. Yeah, so I mean, you know, obviously a lot of gray area in there in terms of what we call a pilot. So where we are at the moment on the ethylene project is scaling that up to 1,000-liter reactor scale, which is to a certain extent piloting validation in terms of having commercial field-based demonstration or piloting in the field. That will come after we've completed a significant runtime on the 1,000-liter. On some of the other projects we're working on, some of them are a little bit simpler to do, and we're hoping to be able to expedite that pathway. And I think the one area that we as the engineering and also the scale-up team have been working on and is really beneficial for our type of process is that biology over 2.5, 3 billion years has become rather specific in terms of the conditions it likes to grow in. So it typically likes them to not vary too much, which means that actually building a pilot plant is most probably not the hardest thing. The hardest thing is doing the genetic engineering. We'll actually be able to do continuous improvement and drop improved microbes into a pilot plant as they become available. The process itself, the engineering part, will not change so much. And for someone coming from a catalyst background, that's a bit of a mind shift, because working in the catalyst field, it was always your catalyst and your reactor need to walk in step, otherwise you can't take massive productivity improvements. Yes, sir.
It seems like in a biological system, one of your main factors for scale-up is going to be rate of reaction.
Yeah.
Can you talk a little bit about that, how you're going to manipulate rate of reaction to scale up?
So the rate of reaction is obviously key to scale up, and obviously directly linked to temperature at which you operate. That's just the thermodynamics of it. So there is a certain limit. We're never going to be running microbes at SMR type temperatures. That just isn't a reality unless Trong tells me he can do a lot more than he's currently been doing. But we do see the ability to work with some of the extremophiles, and Trong, I can always ask you to step in if we need any of those details. But extremophiles do offer us significant improvements on temperature. And then I think the corn picture, while really visually captivating, is really the reality of a lot of what we see. So a lot of the biological processes that we see and that we know about are not optimized at all. Through that biological process is by no means a planned optimization. It's really just a messy, whatever works, we'll kind of keep it, which is why we have veins going from our brains through our chest just to come back up to our larynx. And so what we find is a lot of the manipulation can actually get rid of some of the superfluous fluff and get cut straight to the meat in terms of what we're trying to achieve. So once again, the short answer, GMO for CO2, the short answer is that orders of magnitude improvement are actually not that far-fetched in terms of synthetic biology. Yes?
I have a question. What is your source of endothermic heat of reaction? Because photosynthesis is really neat, because the whole source of endothermic energy is sunlight, which is free. So what is your source? And obviously you're going to need a lot of endotherm, because all the exotherms from burning carbon you're going to have to recover by endothermic reaction. So what is your source of endothermic heat of reaction?
So, sorry, and maybe just make sure that I kind of get that. So in a lot of the processes, the CO2 into a substrate process is obviously exactly as you say. It makes direct use of light, and that light is a variation between natural light and electrically provided light. And that's very much dependent on the location, dependent on the requirements, and also dependent on your long-term forecast of renewable electricity and where that lies. But essentially, we've worked across the entire spectrum all the way from 100% sunlight to 100% electrically generated light. Once the substrate has been formed, in a second step, that substrate can then be broken down, once again through microbes, into any of those chemical components. And then it's really a trade-off. Some of those chemical components are significantly lower in energy level than the substrate coming in, and there's cooling required. Some of them not as big a change. So it really is a case-by-case specific answer, and in terms of the power, in terms of the energy input, it really is a client-by-client and geographic location specific answer. Sorry, there was a question right at that table from the beginning that I've been ignoring. Sorry.
I noticed you said in your scale-up 1,000-liter capacity, but that's still very different from 1,000 barrels a day. Someone producing petrochemicals. How do you see the next level scale-up going?
Yeah, I think that's a fair question. So scale-up's always tricky, right? I've been part of scale-ups that went from 100 barrels to then a 20,000 barrel reactor, and the lessons you learn all have a scientific answer once you've learned them, but you unfortunately have to learn them the hard way to be able to interpolate back to what you should have known. So on some of the larger scale facilities that we're looking at that will truly be disruptive, there are going to have to be several scale-up steps. There'll be 1,000-liter, there'll be an in-field demonstration, and then there'll be the first-of-a-kind rollout. In some of the other industries and some of the smaller facilities, we really do find ourselves having a solution that could really be applied very neatly to modularization. Because we operate at fairly benign temperatures and pressures, the materials of construction are not going to be an issue, so we'll have cheaper materials of construction. The modularization, because a lot of the microbial processes are actually so similar, there's photosynthesis and there's fermentation, it will allow us to really condense a lot of the development and engineering work, which is obviously a key to having successful modular rollout. And then I think a lot of what we see in the renewables industry is with some of the more complicated processes like Fischer-Tropsch, trying to roll that out to every landfill and every wooded area is difficult. You're talking about an incredibly complex renewable process that you're now trying to build up from the ground in areas and with teams that have not been exposed to it. A lot of the process that we're working with is actually not that difficult, and so modularization and the ability to then distribute that and convert something like CO2 into a readily transportable liquid at thousands of locations lends itself really neatly to a hub-and-spoke type of application and modularization, distributed production. Yes?
So a moment ago, Frank had a question on energy balance. I'm going to throw you a question on material balance. And so if you want to, you're a chemical engineer.
I know, I'm feeling the brunt of these. Doesn't anyone want to know about DNA?
I noticed you're converting CO2 to ethylene. And when I look at that, now you didn't write the formula for ethylene there, but as I recollect, it's carbons and hydrogens, right? CO2 is carbons and oxygens. Somehow there's a sort of atomic balance problem there. So could you somehow, I presume microbes do magic or anyway.
So I'll keep it generic and fairly simple, because if I try and get too complicated, I'll step in the mud. So essentially the first part of the process, as we spoke about, utilizes light source as energy and CO2 as feedstock. And then, as you rightly pointed out, there's a missing component there, hydrogen. The natural process of taking CO2 and converting that into a substrate, say sugar, is to really take the carbon from the CO2 and hydrogen from water, combine those with the energy that's being given to it, and produce the substrate material. And so we're really doing the same thing regardless of how tweaked our substrate is. It's still a mix of carbon, hydrogen, and sometimes a bit of oxygen. And so it's perfectly suited to be able to get it from CO2 and water. And then once the ethylene, once the second step, and in this case ethylene, breaks that down again, then obviously there's a water balance that needs to be closed, and there's obviously the hydrogen that's been pulled out of that.
But and effectively then you'll be releasing oxygen as your photosynthesis.
Correct, that's right. So if you kind of, so to keep it simple so that I can follow it, if I draw the big black box big enough, I've got COHO, C and H coming out the one side and oxygen coming out the middle. Yes, sir.
My question was more on the economics of the process. I'm assuming you guys extract the CO2 from some point source, separate that, versus you ethylene that's the product. I don't know what the price of ethylene is in the market. How is that an economic process?
So it's a good question. I mean, and it's the question that all renewable people get asked is, so how do you pay the banker? So I think, as Kevin said, in terms of development goal set, we have set those genetic targets to bring us to a cost parity with traditional operation. And at the moment, we're getting the CO2 as CO2 readily available, aggregated by the client and at a point source that they're looking to do something with. In terms of the broader economics, in terms of the broader economics, if I take, for example, sustainable aviation fuel as a fuel has the same value as gasoline that we put into our cars, but then through things like the RFS system as well as the LCFS system, they add 2 times up to 4 times value to that molecule. And so essentially, in the renewable space, the pressure that all of these systems are putting onto the cost of renewable molecules does translate across the industry, because I can use a renewable ethylene molecule to make aviation fuel or to make plastics, and economics are going to dictate where that molecule goes at the end of the day. So broad-based economics, long-term view is to be at a cost parity or below. Short-term goal is using the credit system that is currently available, as well as growing support for green-based chemicals and premiums attached to those. Yes. Please be DNA. Great question, and it gives me a break. Tron, you're up.
Thank you. For now, so for most of the time, we use like mainly prokaryote cell, but it's kind of a very diverse range of microbes that we have. So we use some kind of model organisms like E. coli and baker yeast. Some of them, for example, like photosynthetic microbe, and then some of the extremophile. From the mammalian cell, I mean, because like most of the time they're very similar, what we can do is like we can take a gene from the mammalian cell system, eukaryote system, and then we can put it in prokaryote to gain the capability that we want. Yeah, thank you.
Just one last one. My experience with biology comes only from water treatment. So if you want those little critters to work for you, you have to keep them happy. So you have to keep the environment so that they keep working, and if you mess up, they get unhappy and die. So do you also have to control the environment that your microbes are working in to certain conditions? And if yes, how do you intend to do that when you send them on their jolly journey to the center of the earth?
Go for it, Thank you. And that's actually part of where that that scale-up process comes into play because we work the problem from both sides. We take the engineering data and the pilot plant data that we're gathering, and we tune the environment. We adjust conditions within the plant to make sure that we can keep the critters happy. But at the same time, that feedback is going back to the scientific team, who can take that information and design molecules that can exist in more extreme conditions, or be happier, so we can bring the plant to the microbes, and we can bring the microbes to the plant.
And you can also get this effect where you have to feed the bugs, right, in order to get them to eat something. But you can run them in a slightly starved condition, and it's going to change the way that they grow, the way that they produce chemicals. So you can almost think of it, almost if you think of it like an engine, you can run it lean or you can run it rich. And it's going to change the way that the bugs grow and how they behave within that environment. So there's a couple of different levers that we have to kind of get the bugs to do what we want and stay alive.
Okay, thank you.
Andrea?
Yes. Many biofuels projects suffer in the economics because of the downstream separation process. So it would be question to ask what kind of selectivity and eventually yield of ethylene you get from your CO2, and have you accounted for this downstream separation process, either in gas phase or whatever phase you receive it?
Yeah, that's a great question, and unfortunately, I'll have to answer that one, seeing as my initial chemical engineering was in separation. So, I mean that's part of the cost of the process is separations. I think it's very much dependent on which product line we're looking at. So, in something like ethylene, the selectivity is key to the economics, and it's one of the key target variables that the genetic engineering team is working on constantly improving. So, in fact, regardless of where we are in the development pathway, they will constantly be working at that, because even once a facility is built, improving that selectivity will, if not save us the capex that's already installed, it will save us the opex, which is a large part of the end cost. In terms of separations, some of the separations compared to fossil-derived molecules are easier. So in some of the processes we've been working in, where some of the fossil-derived molecules are derived through cracking, and you typically have that nice wide spread of molecules with some of them close to your target molecule having very similar properties, which means that your downstream separation needs to be tall and have a lot of reflux and pump around. We are fortunate enough that through the microbial process, you don't see that same that same similarity of products and byproducts. They tend to be very different from each other, which does, if not eliminating separation, does at least make itself a lot easier in terms of separation. But the selectivity is absolutely key, and is a target development that's going to most probably be going on even once the process is licensed. It would be the generation 2, generation 3 would be focused specifically at selectivity. Good.
Looks like we've run out of questions. So
well, once again, thank you, everyone. Really appreciate it.
And we have some parting gifts for you. Oh, wonderful. Thanks. Sure, we give you those.
Thank you very much. Appreciate that. Thank you, everyone.
So with that, I think we're about ended with our November meeting. We will meet on, let me make sure I get this right. Our next meeting will be on December 3rd, and the location to be notified, and we are looking for suggestions for the best location. So anybody with ideas, share it with Eureka and me. So thank you all for coming. Appreciate your attendance. Thanks.